Right. Okay, so yesterday we talked about the role of diffusion for separation. Okay, let me try to put it into a full screen. Make it a slideshow. And just for you know, I think it might be a good idea if you can print the PPT, yeah, the PowerPoint, because for the next few weeks we will always working by hands. Yeah, usually in the class. If before the pandemic, I always use the whiteboard and then use a lot of writing on the board, because all the step by step that I will explain to you, you need to do it. You need to have a hands-on experience. Yeah. So I'm gonna upload a lot of PowerPoints during the weekend, and then if you can, it would be good if you can. If you can print some of them, especially for later on for distillation or absorption, because there's a lot of hands-on calculation. Yeah, or also there would be a number of worksheet, like a template worksheet, so you can do hands-on calculation. You will need papers. You will need the worksheet. You also need pencil or coloring spidol, yeah, or coloring pen. I bought this a lot of colors, like uh, this. Yeah, like this. I have a lot of colors, and then this might be helpful later when you draw the graph. Yeah, because later on you will draw a lot of graph, and for example, to calculate the stage for the distillation, and then if you can have it using different colors, and it would be easier for us. Okay. Okay, so this is quite animated, so let's continue. So yesterday we talked about an example of diffusion. Yeah, how the OPD, operasi perpindahan diffusional, yeah, or diffusional separation. So for example, in distillation process, we just want to bring a mixture with adding a separating agent. For this case, the separating agent is an energy or heat into a two phase. Okay, so once it goes into a two phase or a vapor and liquid, then we can separate them. Okay, so that's the idea. So we really try to use the nature, yeah, the natural force, yeah. For example, the vapor and the liquid, of course, it should be we want to bring out there.
Excuse me, bro. Yeah. The PPT is not showing if
Oh.
You're actually showing.
Right. Let me try to end show. Can you see my screen now?
Yes, bro.
Okay, so let's try to do it again. How about this one? Still in presenter mode, yeah.
We can see it on full screen, bro.
You can see them full screen?
Oh wait, it's weird, bro. Now it's black again.
Oh really? Okay.
Yeah.
How to do that then? Let me stop share, and then let's have a full screen. How about this one?
Yeah, we can see it.
Okay, is it full screen now?
Yes, it's in full screen.
Okay, good. Right. So here, why? How to choose if a mixture of substance can be separated? Usually, we're gonna see the volatility. Yeah. So just to remember it again. Okay, volatility or alpha is the mole fraction of A in a vapor phase in equilibrium divided by the mole fraction of A in the liquid phase. Okay, so like you learn in the the chemical engineering thermodynamics. So this is the volatility, and then if there is two substances that have a different volatility, then it would be easier to be separated by means of distillation. Okay, so that is the distillation. This is going to be the first module that we're going to learn. And then the second one is the absorption process. Yeah, in the absorption process, you have a gas that contain a solute or S here. For example, we have 1% of carbon dioxide in natural gas, and we want to clean the natural gas. We want to remove the CO2. So we're gonna put it into, we're gonna put the natural gas into an absorber column. So the absorber column is also very high. Yeah, it's like a tower. Okay, so if you see the Edunex, and then I put the picture of distillation column, which is very tall. Why it's very tall? Because later on in each inside the tray there is a steps. Yeah, so for example, if we calculate the step, okay, it is a half a meter for one step of separation, and then we calculate we have to we need, for example, 20 steps of the distillation. Then we have to just multiply the half a meter multiply by 20 stages, so around 10 meters. Okay, so that's why the distillation column, also absorption column, is quite high. Yeah, so it's like a tower. Okay, so here so then we're gonna get the clean gas, and the solvent. The solvent now will have contain the CO2 in a pregnant liquor. Okay, and then from after the pregnant liquor is going to go to another column, or the we call it stripping column, and then to remove the CO2, and then this can be released or use it for further processes. Okay, and then the last one, this is liquid extraction process. Sometimes in the book, in the Seder book, sometimes if there is two or three component or substance, sometimes it can be removed by distillation, but sometimes it can be removed by extraction. But sometimes distillation is not preferred, because in distillation we use heat. Yeah, we use energy. We heat it up the solution. Sometimes some solution is it can't be heated. For example, essential oil. Yeah, if you heat it too much, for example, then maybe some of the organic compound gonna be rusak, broken, or and then also it's not going to be good for the substance. Then we can sometimes we can use also a liquid extraction. Yeah, so the principle is to put a separating agent, but for this case the separating agent is the liquid, not the liquid, where the solvent compound is easier to dissolve in liquid. Yeah, I'm not sure, but did you do organic chemistry lab, or only watching the practicum?
We only watch, Bu.
Yeah, we only watch.
You only watch it, so you didn't do it by yourself, yeah. Since long time ago, we always do practicum to get the tein, yeah, the component in the tea from in kimia organic always, yeah, from when I was in kimia organic, when I was in the second year, and also I think some of your kakak tingkat, yeah. But then I'm sorry, you just only need to watch, yeah. So basically it's similar to this one. So basically we have the hot the tea, yeah, the tea bag or the tea leaves, and then we dissolve it with hot water, like a boiling water, and then so everything is dissolved. The tea component is dissolved in the water. Okay, and then we want to get the crystal of tea. So the next step after we boil them into the hot tea, then we get the hot tea, and then we mix them with organic hexane. Yeah, so I think that if you know, there is like that, yeah. So we mix them between so this is some, I forgot the name, but this is for the organic for the organic extraction. So we put, so for example, this is water and tea, and then this is hexane, yeah, or the organic, because of the bonds or because of the component in the tea, they love hexane, like non-polar, very much. So when we mix them, then it can so the tea will yeah, so the tea will dissolve in hexane. Okay, so that's why in extraction there is we call it mixer and settler. So usually there is we call it in extraction is mixer and settler. So we have to mix them. So those two liquid will mix together, and then there is a contact between liquid L and liquid P, and then they contact together. And during the contact, then the solvent will transfer, yeah, from the liquid L into the liquid P, and after that we're gonna settle them together. Okay, usually they have different density. The organic one is lighter compared to the water, and then they just gonna settling, and then we can get the tea rich in the hexane, and after that we can dry them, or yeah, I think just dry them, and after that we will get the crystal of tein, yeah, tein for the tea. That's just some example of liquid extraction process. Okay, so from those three examples of separation, okay, just put it there. Okay, so for phase equilibrium, it is a natural process. We can't deny that. And then we will do everything we can to just use that force. Yeah, if the natural process, for example, gas will be always go flow upwards. Okay, so then when we separate gas, we're gonna maybe just let the gas vaporize, and on the top of the distillation column we will install a condenser. Okay, so all the vapor will be condensed, and then we can collect it as a liquid. Okay, and then while the liquid will always flow downwards, so of course the heavy components will go downwards, and then we can have a boiler at the bottom of the distillation column. Okay, so we always use the natural process. Okay, and as you know, because we use a lot of equilibrium composition. So the equilibrium composition is a function of pressure and temperature. Yeah, you have learned in thermodynamics about how to calculate equilibrium composition in different pressure and temperature, and then we also use that one. Yeah. And then so the equilibrium composition is based on experiments, as there is a huge amount of experiment since 1930s. Yeah, since all the chemists, all the engineers, they experiment with the crude oil, with many chemicals, yeah, benzene, toluene, and so on. So for all chemicals that use widely, we have all the database, yeah, and the database is stored in a software, for example, HiSys. Okay, and then from all of the data, then the engineers make the model to predict the thermodynamic properties. Okay, so as you learn in statistics, if you have a different set of data, and then you can do interpolation or a little bit of extrapolation, and then when you predict properties at certain condition, then you can use those models. Okay, so in this for example, HiSys, yeah, or a software, they also use the same. So we also can calculate it using a model. We can predict the thermodynamic properties. Okay, in thermodynamics, you also have learned about, for example, if using Margulis model or using Peng-Robinson, and then you can predict the composition if you know the pressure and temperature. Okay, so there's something like that. Okay, but if we deal with new components, for example, we found new essential oils, let's say, and then we want to do the separation, and we don't have the data, so that means we have to do the experiments. Yeah, we have to do the experiments to get some certain data points for the equilibrium points, and then after that we can make a model and then predict them. Okay. The factors that affect equilibrium composition, of course, the equilibrium condition and also process configuration. Okay, so this is also for the use of differences on diffusion rate. This is, for example, for a membrane. So like I explained yesterday, this is the mixture of A and B, for example, 50%, but B is more permeable, A is more permeable compared to B. So then A is more, so A will transfer into the other side of the membrane, right? So then in this side, you will find a concentration A is higher than B. Okay. Okay. So for membrane, usually the separation medium is based on a polymer material, while it looks like a plastic or look like a polymer, but when you see in a micrograph, a very small, like nanometers or microns, you can see a hole in it, yeah, and then those holes will allow the gas the gas or is to escape. Another example, very small, maybe a simple example of membrane is a balloon, yeah, balon udara. Okay, so if you blow a balloon and then you just tied it and just leave it for a while, after 1 week, the balloon will not as big as before. It's just gonna stretch. Yeah, it's because some of the air or the air inside the balloon will escape outside, yeah, through those balloon membrane, yeah, from the rubber membrane. Okay, usually the driving force is the concentration gradient and also the pressure gradient or electrical charge gradient, yeah, and then the defining factor is the separation separating medium and process configuration. Okay, so for this membrane Professor Wenten, Pak Udin, Bu Anita, yeah, is more experienced. They have a renowned world research in that area. So maybe at the end of the semester, when we have more time to do more courses after we finish the extraction, we can bergabung, ya, we'll join the regular classes together and then to learn about the membrane. Okay, so that's okay. So then the next session we'll discuss about the distillation process, absorption, liquid extraction, and separation by using membrane. All right. Before I change into the next slide, so I'm gonna ask if you have any questions.
Actually, Bu, I have a question, Bu.
Yeah, okay, Kevin.
I'm still confused, Bu. In the CO2 stripper, like how does that happen? Because all you said was just like the CO2 just escape, right? But how does it actually got stripped from the MDEA, if I'm not mistaken? Is that right, Bu?
Yeah. Usually in the H2O in the CO2 stripper, we change the pressure and temperature. During the absorption, usually absorption is happened on the with the pressurized condition. For example, 10 ATM or 15 ATM, so it should be pressurized, and also the temperature should be lower. Okay, like if you have Coke, then you want to make it Coke as cold as possible, so it refresh because it has a lot of CO2 in that Coke. Okay, so so during a low temperature and also high pressure, the CO2 will be absorbed to the liquid. Okay, Kevin? Yeah. Hello.
Yes.
Okay.
Yes, Bu.
Okay.
Hello.
But then, yeah. Okay. So then we have a liquid. We have the MDEA that have a lot of CO2, and then we're gonna put it into another column where we change the pressure. So the pressure, we're gonna lower it into the atmosphere, and also the temperature, we're gonna make it a little bit hot. Okay, so at that time for the equilibrium, then the gas will release from the MDEA. Okay, yeah. So that's the principle. So that's what we call in one of operation there is a term that named PSA, or pressure swing absorption, or pressure swing adsorption. So how the gas can absorb or how gas can release from the liquid easily changed by the temperature and pressure. Okay, Kevin. Okay, very good question. Okay, any other questions?
Okay, well, thank you.
Yeah, while I'm preparing the next slide. Okay. So now we're in a segment 3. Oh, so now we let's go to the segment 3. Yeah. Okay, let's try this one. How about this? Can you see the full screen or presenter view?
We can see the full screen, Bu.
Okay. But for me it's not a full screen, so can you see my pen?
Yes, Bu.
Yes, ma'am.
Okay. All right. So let's go back. Yeah. Okay, so now we're gonna learn about vapor liquid binary mixture because we need to talk about distillation for binary distillation. Yeah, so the principle, because the distillation based on the equilibrium, so we need to learn just to refresh our knowledge about vapor liquid equilibrium. Okay, so this is a vapor liquid equilibrium for one substance. Yeah, so for one substance. Okay, so this is the pressure and this is the temperature, and then for example for water, this is the for example let's say at certain pressure here. Okay, so in a fixed pressure, then for example we have a liquid, and then if we increase the temperature, and it's gonna be a vapor. Okay, and then and this one is the gas, this is a vapor, sorry, this is the liquid. Okay, so this is a salt, the one that we're looking at is the liquid and vapor. Okay, and what is the difference between vapor and a gas? We can clearly see on this graph. So usually gas is the where it has a very low critical point. So during the ambient temperature, it has a phase of a gas. Okay, but vapor is still have a but in vapor here you still can change into the liquid. Yeah, you can it can interchangeable with the liquid if you lower the temperature. Right. So okay. Yeah, okay. So let me describe one by one. Okay, so let's say we have a component A. Yeah, the component A is a has high volatility. Okay, for example, we have acetone. Yeah, you know acetone, the one that you put into the Q-tex. Yeah, if you want to clean the Q-tex, if you just put it on the a piece of plate, after a while, or after a while, then it's just gonna gone. Yeah, because it is very volatile. Or maybe a perfume, for example. Yeah, this for the perfume, if you just put it like that, and then I leave it for a while in my hand, then it's just gonna vaporize into the atmosphere, because it is very volatile. Okay, so here in a component A, which has a volatility at for example in oops, sorry. Okay, put it like that. Yeah. Okay, so here for component A, for example, at a certain temperature from the liquid, if we increase just a little bit the temperature from this point, for example, at a similar pressure, it's easy to vaporize into the vapor phase. All right, and then let's have a look. We have a component B. Yeah, component B, or the blue one, is less volatile. Okay, so the component B has low volatility or less volatile. This is still in the liquid phase, and so after a while, then it can goes into the vapor phase. Okay, so if we have a look, let's say, for example, in TA here, or yeah, oops, sorry. Maybe change the color. Okay, so let's say, for example, let's have a look on this T over here. the green one, yeah, this point and also this point. Okay, A, what is the phase of A in this point? Is it vapor or liquid?
Vapor, Bu.
Vapor. How about the B?
Liquid.
Liquid. Okay, yeah. So that's why A is more volatile compared to B. Okay. So then after, if we have maybe increase the temperature more than TB, so then both of them can be vapor. Okay. So so that's the two different properties, yeah, between A and B. Now, what happened if we mix them together? If we mix them together, the diagram, and then we put it into one diagram here, and then if we combine them together, then it becomes like this. Okay, so A is the line, the red line here is the line of the equilibrium between the liquid and the vapor for component A. And then the blue one is the vapor liquid equilibrium for component B. Okay. Yeah. Any question up to here? Right.
So, Bu, I have a question, Bu.
Yes.
So, they're mixed together, like, but you are given at temperature, the one that's green, the one in between. Even though it's mixed, the red line will evaporate first, right? Even though they're mixed, like it won't have like a difference in like yeah, like the lines won't mix or something like that, right?
Yeah, that's right. That in the next slide, yeah. Okay, so this is, I just combined the two graphs together. So so like Kevin said, so what happened with the binary mixture? So what happened in the binary mixture? If we combine them together, then it's actually it's gonna be like a mixture. Okay, and the mixture would looks like the green one here. Yeah, this is very small in me, so let me make it bigger. Okay, this one's better. Okay, okay, so this gonna be looks like the green one. So let's say, so if it is a mixture of 50% mole of A and 50% mole of B, so what happen is it won't have a two different, if we have a mixture 50% mole of A and 50% mole of B, it won't have a separate graph, but then we will have a new graph like the green one here. Okay, so what happened from here, this is all both of them gonna be a liquid, and very small here between the two line of green, there would be an area of, we call it two phase. Yeah, there is a two phase, which is there is a vapor and also a liquid. Okay, there is a two phase there. And after that, after the green one here, and then it makes all of them gonna be liquid. Okay. Let me read the in Indonesian way, yeah, the text. So let's say, so campuran 50% senyawa A dan 50% senyawa B secara ideal, kurva kesetimbangan uap cair, so this is a vapor liquid equilibrium, akan berada di tengah-tengah kurva senyawa A dan kurva senyawa B. Namun kurva itu tidak akan dalam bentuk garis. So it won't be like a line like in before, but it's gonna be like an area. Okay, so then if you make this is still a little bit small in me, but then there would be an area here inside the green one where the area is in the two phase vapor liquid mixture, campuran uap cair, yeah, vapor liquid mixture. Okay. So then it gonna start from the T bubble and the T dew. Yeah. Did you remember about tea bubble and the tea dew?
I think I still do.
Okay, right. So the tea bubble, we call it it's saturated liquid, yeah, tea bubble. If we have a jar full of liquid, and when there is one bubble of vapor, it's called the tea bubble. So tea bubble is when it is saturated liquid atau cair jenuh, yeah. So the tea bubble, and the tea dew is when you have a room full of saturated vapor, and when you just lower the temperature a little bit, and that would be one drop of dew, ya. Ada satu uap jenuh, so that means the tea dew. Okay, so so that means the idea of this graph tells you that for a binary mixture, you don't have one line for the interface, yeah, between the vapor and liquid, but you have one area of the vapor liquid mixture. Okay, so let's see. Okay, yeah, so that would be, so that would be looks like this. So here for 100% A, okay, so so let's say we have A and B, yeah. So 100% A or 0% B, we use the red one, okay. So 0% A, which is 100% B, so we use the blue one. Okay, so if we mix them together 50%, 50%, then we have this line, we have those areas. So it looks like an envelope, yeah. So let me, so maybe it looks like an envelope like this. Okay, so maybe there's a line for the blue one and also for the red one, for example, that area, and then this is the envelope, and this area is the area for mixture, yeah, mixture of liquid and vapor. Okay, and then let's have a look again. If we have a tree diagram, oh, okay, so we mix, we have a 3D diagram between the pressure, okay, between the temperature, and also in the composition, okay. So the first one here is for 100% A. Sorry, should be, oh sorry, terbalik ya. Okay, or let's say this is the 100% A, yeah, 100% A. So you have the red one, yeah, because 100% of A. Okay, or one here in a mole fraction. So the mole fraction of fraksi mole sama dengan 1, yeah. So this is the liquid one, the liquid and the vapor, yeah. So this is the line. So like we see the before, it start from the liquid and go to vapor, to cair ke uap. Okay. So and then when 0% A, which is 100% B, the blue one, we have also the line there. Okay, so this is the liquid and this is the vapor. And then we can maybe make several slices of pressure and temperature at different mole fraction. Yeah, you can try and then make it, put it here, maybe put it there, but we won't draw it. And then let's also make a sketch on the 0.5, which is a true which is where there is an area. Okay, so this is the liquid, and then there is an area which has a mixture of vapor and liquid, uap cair, and also the lower one is the vapor. Right? Okay, up to here, any questions? Okay, so so that means if we join them together, if we make it bigger, then oops. So, or maybe this one. So it kind of looks like lidah, yeah. It's like a tongue. So if I can draw them later on, it will be looks like that. So this one is aligned. This one is aligned, but around this area is getting bigger, yeah, because there is like this. It's like a tongue. Okay. So that is the tree diagram of vapor liquid binary mixture. So then we can draw something like this. Yeah, we can draw something like this. How if those this tongue lidah ini, yeah, we can slice it with with a constant pressure. With a constant temperature. Bagaimana kalau kita potong dia pada temperatur yang sama? Dia sama, okay? So just try to imagine you have a tongue in a 3 dimension, okay? And then there is a mole fraction for the axis, and then temperature maybe for the z-axis, and then the pressure for the y-axis. Yeah, try to define a three dimension. And then here, and then you slice it with the similar temperature. So that means you will end up with this area. Okay, so if you slice it with the temperature, you end up with maybe like that. Yeah, if I slice it with the temperature, so this is the mole fraction, and this is going to be the pressure. So then, I will end up with this slice area, or maybe like that. Okay, yeah. So this is A. Okay. Istirahat tuh. Okay, yeah. So this one is gonna be, is it liquid or vapor? What is the phase here?
Liquid.
Liquid, yeah.
Yeah.
Okay. What is the how about this one? Vapor.
Vapor.
Okay, and this is the mixture, yeah. This is the mixture. So that's why if you increase the pressure, then it's gonna be liquefy, yeah. For example, oxygen cair, yeah. If you have a pressurized oxygen, then the oxygen will liquefy. Okay, and then what if I slice them with the maybe with the mole fraction? Let's have a draw in the different color, for example. How if I slide it as a mole fraction? Maybe it becomes like that. Okay, so I have a temperature here. Okay, and I have a pressure. Okay, maybe, and then I have maybe this one there. Yeah, like that. And then this is liquid, and this is a vapor. But sometimes we don't often to use this one, because usually the mole fraction is always changing. So we don't use this graph very often. Okay, and the last one, how if we slide it using the pressure. Okay, now I would like to ask you about practical point of view. Yeah, in a column, in a reality, what do you think? Is it easier to change the pressure, or is it easier to change the temperature? What do you think? Is it easier to change the pressure, or is it easier to change the temperature?
The temperature, I think.
Yeah, the temperature is much better because you just install a boiler, yeah, down the very close to the column, and then you can just boiling up those this mixture, and then that become a vapor again. But if you change the pressure, that means you have to install maybe vacuum or a vacuum pump, or if it is vacuum, or if you want to make it higher, then you should have to install compressor in the middle. It's very difficult, okay? Or if the component is let's say, yeah, it's not easy to change or sudden change of the pressure. So for practicality, it is easier to change the pressure, and also keep the pressure, change the temperature, and also keep the pressure constant. Okay, so that's why let's have a look on the next slide. No. So on the next slide, it's much easier for us to do this one here. Yeah, so the vapor equilibrium at a constant pressure. So if we slice them with the orange one here or the brown one here. So we slice the tongue like horizontally at the same at the constant pressure. So then we're gonna end up with, so this is this one is temperature, yeah, temperature, and this one is the mole fraction. Okay, so maybe it will gonna be looks like that, yeah. So it's gonna be looks like that. Okay, so what is the what is the component here? Vapor or liquid?
Vapor.
Vapor, right? And this one would be liquid. Okay, yeah, so this one is the TXY, yeah, the diagram TXY that we often gonna use. Okay, this one is the critical point, yeah, and this is also interesting. This tongue diagram, the 3D diagram, is used for us to determine the pressure, yeah. If you check, make it, maybe I'll make it different color, yeah. So if you go to the lower temperature, you have a quite big envelope there, yeah. So if I can draw it here, if I go in the low pressure, if I cut it, for example, this one, yeah, if I cut it in a low, okay, if I cut it in a low pressure there, it goes to from 0 to 1, yeah. So the composition. So maybe, and I also have a big and quite big envelope. Sometimes we need this. So that means if I have, if I want to purify the A, for example, I have 50% A, and then I want to purify it to 100 A. It is feasible, yeah. It is possible to separate them into 100% A. But when you go into the higher pressure here, it just looks like a tongue. Ujungnya makin mengecil, ya. See the over here, it is make it becomes more smaller, maybe become only this area. Okay, and the area for the mixture of vapor liquid is only in this area. So that means at higher pressure, it's not possible for us to go beyond this curve. And then it's not possible to get 100%. Okay, so that's why in the atmospheric pressure, in the distillation, it is easier for us to do it in atmospheric pressure, at low pressure. Okay, or sometimes we can do vacuum distillation. In the crude oil, there is a VDU or vacuum distillation unit, because we really want to go to lower temperature so we can get those area of separation. Okay, so then we'll see you in the next session. So this different. Okay, so now it's the okay. So it's finished for the third one. Okay, so before I change, or I'm going to stop share first, and then let me know if you have any questions. Okay, we'll still keep going. There's still no assignment for now. Maybe next week when we start to do the fractionation, then maybe there would be a lot of assignments. Let's see the numbers. Okay. How about this one? Can you see the full screen?
It's not full screen, Bu.
Oh, still in here, still presenter view, yeah.
Yes, Bu.
How about this one?
It's in full screen now, Bu.
Okay, can you see it?
Yes, Bu.
Okay, right. Now let's have a look on the detail, the PXY diagram and the TXY diagram. Okay, so this is the one that I was talking about before, the 3D diagram of the area of the mixture, the ideal binary mixture for vapor liquid equilibrium is looks like in this one in the book. Yeah, you can in the book there. So this is between the composition X. X is the mole fraction of A. So this is 0 is the pure B, and this one is pure A. And then the vertical one is the pressure, and then this one is for the temperature. So it's up to you. Do you want to slice it vertically with the constant temperature, or horizontally at a constant pressure? But then we just talk about it that of course it is more practical for us to change the temperature compared to change the pressure. So we usually use this at a certain pressure, at a constant pressure, and then we slice it up horizontally. Then this is gonna be the area. Okay, so like this. So I'm gonna skip this. Okay, so this one is the one if we slice it up vertically, or we slice it at a constant temperature. Just to remind you again, just to remember that this one is the bubble point, the bubble line, yeah. So for example, this is W. W is liquid, yeah, liquid, and then if we lower the temperature up to sorry, if we lower the pressure up to U, it become a saturated liquid, or this is called the bubble temperature. And then if we goes into this side, this is very very important here. Oops, okay, if we goes in here, yeah, if we go to this point, let's say we lower the pressure up to this point, there is no it's gonna be in two phase. Okay, akan terjadi dua fasa. Yeah, the phase would be the liquid and also the vapor. Let's say this is, I'm gonna put it X. Okay, so then in this X, that would be two phase, which is vapor and also liquid. Now, I would like to ask, this is similar with the bahan konstruksi, yeah? What is the, or the left rules? What is the composition of vapor? Can you can you mention which one is the composition of the vapor?
The one to the left, Bu.
Composition of the vapor to the right?
Wait, I think am I mistaken?
Yeah, this one to the right. Yeah.
Oh, okay.
Okay, so V. Yeah. So that would be we called it because this is pressure. Yeah. So that would be the composition of vapor. For composition of vapor, we call it Y of the V. Yeah. At the point V. Okay. And then the composition of the liquid is the T. Yeah. This one T or X or at the point of T. Okay. So and then how about the amount? The amount of vapor. Because this is vapor, then we're gonna use the left rule. So the amount of vapor is this one. Yeah, the jumlah ini. So if this is A, this is B. Yeah. So then fraction of vapor would be the left rule or the yang berseberangan ya. So that means A divided by A plus B. Okay, and then the liquid is the fraction of liquid would be 1 minus this one, yeah, or B divided by A plus B. Okay, and then up to after that up to 1 point into S. So S would be saturated vapor. Yeah, so S would be saturated vapor. And then if we lower again the temperature, then it's still gonna be in just as super heat, as a vapor. Okay, so usually the mole fraction of vapor is, we call it Y. Mole fraction of liquid, we call it X. Yeah. Okay. The second one, if we do it in the constant pressure, yeah, like I said before, we often use in constant pressure. So let's have a look this one. So this graph is very important. It may be in the assignment and also in the exam. Okay, so pinpoint this one. Have a screenshot, and then this one you need to know also. Okay, so right here, oops, where is it? So this one here is the a vapor, okay, O, and then when it if we lower the temperature, it goes into the M. So M is this one saturated vapor or saturated liquid? M.
Saturated vapor, Bu.
Yeah, saturated vapor. Good. Okay. And after that, we gonna cool it down a bit up to this temperature. And then it goes into the two phase, vapor and liquid. Ya, ada dua fasa cair dan fasa uap. Okay, and then here you can see that the vapor phase will have a composition of K, while the liquid phase will go into the composition of L. Okay, you can read it after that. Okay, so you can see down there to see the composition of this is liquid, yeah, so XL. Okay, and if you want to calculate, so okay, what is the composition of the vapor that we get? That is, okay, so this one is YL. Okay, this is important principle for distillation. So that means if I want to separate for example, I have a vapor, yeah, a vapor with composition of O, for example, yeah, and then I want to separate them. Okay, I want to have a phase that reach in A. Okay, maybe I can just cool it down and then put into a flash drum. yeah, a flash separator. So the name is flash separator. Yeah, later you will, I think you have learned in perawatan process, yeah, how to design separator. And then if you at the temps at some temperature, maybe this temperature, okay, and then keep the pressure similar, and after that it will have a vapor phase. So then we can this gonna be vapor phase with the YK. Well, then it will have a liquid, yeah, we have a liquid with the XL. Okay, so then we can separate, so we can just separate YK into, I don't know, maybe for the further processing, and then we will have a remaining of XL. Okay, so this point, yeah, this actually shows you like one stage of separation in distillation. Okay, so I'm going to try to stop it, and then let me know if you have a question. Any question up to here? Yes?
Bu, I have a question, Bu.
Yeah, okay, Kevin.
So the YK and XL, that is the thing where like you want to find the mole fraction of gas and liquid gitu, Bu.
Yeah.
All right.
Okay, so this is K, and then you look at to this one, yeah, to the mole fraction, and then you can read it. So this is before 0 and 1, then maybe this one is somewhere 0.6 something. Okay.
So if you add them up, it will be 1, right, Bu? The
No.
YL and XL. No.
No, it won't be 1.
Why is that, Bu?
Because oh yeah, very good question. Why YK and XL, if we added up not one, why? Very good question. Because this one is not if you want to get it 1, maybe we can get 1, but the 1 is for the amount, ya, jumlahnya. Okay, so let's see this one. Do you remember Lever's rule? Yeah. So let's say this is A, this is B. Okay. So let's say I'm gonna have, for example, this one is 100 kilogram. Okay. So how much the vapor? How much is the vapor that goes into the vapor phase?
A, Bu.
Yeah, A divided by A plus B, yeah? Oh,
Yeah.
A divided by A plus B multiply with 100. Okay, so that is the vapor. Okay, and the liquid, you know that this is B divided by A plus B multiply with 100. So the neraca massa, yeah, or if we call it, this is feed. So the neraca massa, we know that F equal to V plus L. Okay, so the neraca massa, yeah, or the mass balance. And then the second one is the neraca component or the component balance. So that means if we look at the component A, for example, weigh A in the feed, okay, and then equal to the vapor phase of A in the stream K, multiply with the vapor, the multiply of the vapor, the YK, yeah, and plus X A in the L multiply with the L. Now, this one is gonna be 100. Okay, so 1. So if so Kevin asked, so why is that why? So YK plus XL is not equal to 1. Won't be equal to 1, but what is equal to 1 is the component balance, ya, neraca komponen. Okay.
Yes, Bu, I understand.
Okay. Yeah, but that's very good question. Okay, and then we're gonna use a lot of mass balance and also component balance later on in the distillation to make sure that our component A, yeah, would be balanced, of course, in the vapor phase and also in the liquid phase. Okay, so this one is actually the basic of distillation, yeah, the basic of one stage of distillation. Okay, any other questions? Okay, let's have a look the next one. Okay, so usually we also plot a graph, yeah, because see, YK and XL is not equal to 1, but every line has a pair. Masing-masing punya pasangan, ya. At a certain temperature, everyone will at one constant temperature, it has one pair between the Y and between the X and Y, X and Y, X and Y. Okay, a pair. So it won't be equal to 1, but it can have a pair. Okay, so the next one here, so because this is the graph of Y and this is the graph of X, and then let's have a pair up to like this. Okay, the constant binary, if we plot the X and Y at one point, yeah, at one point, it's gonna be looks like this. Yeah, so this is an ideal binary mixture phase diagram of the mole fraction A in the liquid, or X, yeah, and also Y, yeah, the mole fraction of A in the vapor. Okay, for example, at one certain temperature like this, okay, this is the vapor liquid equilibrium. What is the composition of the vapor? How to read that? We see the mole fraction on the vapor. So then let's have a horizontally. Okay. What is the composition of the mole fraction in the liquid at this point? So then that one there. Okay. Okay. So that is the XY diagram. So from this diagram here, I can make also an XY diagram. So let's try. Yeah, let's try to make XY diagram here. Maybe with the color of red. Yeah. So I'm gonna put it. Maybe this is X. Yeah. This is X. And then this is. Okay, sorry, it's not okay. Make it bigger. Okay. Okay, let's say this is a Y and this is an X diagram. Okay, this is the line that tell you that X equal to 1 at a Y. So like a control, graphic control, yeah, a control graph. So this is Y equal to X. Yeah, come on. Okay, for example, this is the X, this is the Y. Okay, so if I have the X here, like the magenta, yeah. If I have the exit, so I'm gonna use perkiraan, ya. Sometimes in the whiteboard I use my hand, pakai tangan, ya. Try to memperkirakan how much is it, okay? This is engineering way, ya, engineering judgment, cara engineering untuk how to try to predict, memperkirakan how much using your eyes and also using your hand. So here, let's say this is 0, this is the 1. Okay, so for example, here when X equal to 0, L also equal to 0, right here, yeah. So I'm gonna put this point. Okay, when X equal to 1, Y also equal to 1. So I'm gonna put this line here. Okay, And then when I see X is equal to this side, maybe around this one. So I'm gonna put it there. Okay. And then Y is around more than a half, yeah? More than a half, maybe around that one there. So maybe Y is more than a half. So if this is the half, 0.5, maybe around this area. So this is the X, and this is the X, and this is the Y. So the pair would be in this one. Okay, so the pair of this one would be that one. Okay, let's try another one. Maybe let's see the pair between change color, the pair between N and M. Okay, the N may be just a little bit less than XL, so maybe I'm gonna put it here. Okay, so the line, use your ruler, yeah, for you. And then this is the composition of L, maybe around that area, yeah. Not half, but less than a half. So if this is a half, maybe less than a half. So this is 1 point. Okay, maybe one more try around this area. So this is the X is more than a half. So if this is the half, so maybe this one, this is the X. And Y is almost 1, yeah, the Y is almost 1. So maybe around here. So this is 1, so this gonna be point. Okay, so then you can you have this point, this, and this. So then using your hand, try to do interpolation. Yeah, you can make a curve. Jangan pakai putus-putus ya. Don't make a like jangan diputus-putus, but try to make a curve. So then, oops, what is why it's happened? Then you can make a okay, and then make a curve. It goes to this point, goes to this point, maybe to go to this point, and then goes to this point. Okay, so then this is the XY diagram, right? So this is the XY diagram, and it's gonna be looks like this. Okay, so in the next few weeks, you're gonna need you need to do a lot of drawing. So maybe we have to do a lot of practice, yeah, to change, for example, from TXY diagram into the XY diagram. Okay, if you're still confused now, that's fine. We're gonna do a lot of practice like this, yeah, even for distillation or up to extraction. That would be a number of practice on this one.
Bu, I have a question, Bu.
Yeah, okay.
In the exam while we're drawing, can we use a pencil or like we're supposed to use a pen?
Yeah, you can use pencil. You use pencil, and then also we're gonna give you the papers beforehand. We're gonna use the worksheet beforehand. Or maybe the good idea is to use millimeter blocks as well. Yeah, to use try to draw this using millimeter blocks.
Okay, thank you, Bu.
Yeah, but because this is online, then we see it using on the screen. Yeah, so try, if once you use the pencil, maybe you can try to bold it up, yeah, to ditebalkan, so we can see your work. Okay, so this is the one that I'm talking about, that the tongue, that the influence of pressure. If you change the pressure, or if you increase the pressure, so sometimes we can't go into the maximum A that we want. Yeah, in a binary component A and B, the component A is the one that more volatile. Ya, jadi komponen A selalu komponen yang lebih mudah menguap. Yeah, let's say if you have a mixture of acetone and water, then you have to put the acetone as the component A, because acetone is more volatile compared to water. Okay, don't put water as a component A. So for example, so we have an impression that A is the one that we want to get the purity, ya, yang ingin kita ambil. So then this one is good because at this pressure, then it goes from 0 to 1. And so if we started, for example, 0.3% of A, we can maybe do number of distillation to get these points. Yeah, but if we started at high pressure, for example, 0.3, we only can go into 0.35 because up to here it's just finished. Yeah, the vapor liquid equilibrium is finished in this point. Okay, so then when we plot them into the XY diagram, then here it is. This one has a low operating area for the distillation, while the this one goes into 1, and also this one the pressure one has a more area. Yeah, more area is important because we can later on we can change the stream easily. I'm gonna explain to you later, but in a sense, if you have a bigger area and then lebih cembung, ya, then you have more easy to change everything, yeah, to change the operation for the distillation. Okay, what happened with the azeotropes? Yeah, what happened with the non-ideal binary mixture phase diagram? For example, this one with the azeotrope. Then if we have a TXY diagram and then we change it into the XY diagram, that means the area that we have is only up to here. Yeah. So if we want to go further, this one there should be another treatment, maybe adding another reactant, or to break down those azeotrope, or to I don't know, maybe adding some reagent or something. So for example, if you should be in the lab, yeah. But if you're in the lab, you will find a lot of ethanol, 95%, yeah, 95%. We call it ethanol techniques, yeah, because ethanol and water have azeotrope up to 95. So then if you get ethanol techniques is cheap because only need one stage of distillation. Yeah, you can get ethanol techniques 95%. But if you're working in, for example, in the lab, and then you need almost 99% of ethanol, the cost is much expensive compared to the ethanol techniques, because to get more than 99%, they need some special treatment. All right, so yeah, so then this one is the TXY diagram that we're gonna use. Yeah, we're gonna use a lot, and then it's gonna use in the exam as well. Yeah, always use the TXY diagram. So then you need to know how to you need to know how to read this TX diagram, and also to get information from this TXY diagram. Okay. Okay, so let's have a look. For example, this is the ethanol water system. Usually we may get the data. This is the temperature. In one temperature, there is X and also the Y. This is the temperature, yeah, and then 95.0 and so on, and then TXY diagram, and then we can sketch them in the diagram, and it would be like that. Okay, how to sketch them? So this is 100, there is 0 and 0. So then at 100, there is 0 and 0. Okay, and then let's have a look again. At 99 and 95.5, there is the XA is 0.02, while the YA is 0.17. So that means if this is the bubble, yeah, bubble point, cair jenuh, yeah, saturated liquid. So at 0.01 XA, maybe this one, and then YA is this YA is this one, okay, like that. And then you can go, you can try it if in your spare time. So at one temperature there, okay, everything has a pair of the Y and also the X. Okay, anyone? Do you have any questions? Still confused with this one? Can you do annotation in here? How to no, can you see annotation in Zoom? No, yeah.
Not yet, ma'am.
Not yet, yeah. How to do you know how to do it?
Not really sure.
Okay, I will ask my staff, yeah, how to turn on the annotation. So later you can try to draw as well. Okay. Okay. Damalia. Damalia, what should I do if I want, for example, this one at 80.7, the XA is 0.4 and YA is 0.61. Can you point out what is the when the temperature is 80.7? 80.7. So which one? This one, yeah?
It's near the idea.
Okay. So let's have a look at that one. Sorry. Okay, so maybe this one, yeah. So can you read that one? And this one is that one. So
the XA is 0.4.
the XA is 0.4.
Yes.
Why is different, yeah? Yeah. Kita kebalik ya. Or maybe it's different graph, yeah, from here. Yeah, but okay, just let's read the graph then. So for example, just using this graph at 80 degrees Celsius, then you can read the XA, yeah, maybe around 0.27, maybe, yeah. Okay, and can you read the YA using this one, this screen?
0.57 perhaps.
57, yeah, you can say that, yeah. Okay, and also because you just gonna see it using your eyes, there would be a lot of error, but that's fine because we just gonna see your work. Okay, if your work is like this and then you say it like Dama said, okay, maybe 0.57 or 0.56, yeah, that's fine. So everything's correct 100%. But if you said it like this and you said, Bu, this is 0.6, yeah, it's too much different, yeah, using your eyes, so then it's not going to be correct. Okay, let me check. Okay, so here around after this 95, actually there's a little bit of azeotrope, yeah, so it's difficult to find. Okay, so when we plot it into the XY diagram, it's gonna be looks like this. It have a big area at the bottom, but then very tiny in here, yeah. So then for ethanol and water, we only can just finish it. It's all for around 90 or 95, yeah, around 90 for this case. All right, let's finish again. So I think up to, okay, so I'm gonna keep the ink, and before we go to the next session, I'll wait a minute. Okay, and then PXY, TXY, and then let's find the XY analysis. Okay, now let's see the TXY diagram analysis. Okay. Give me 1 minute. I need to check my kids to go to the Google Meet. Yeah, just 1 second. Aisyah, ada Google Meet. Okay. Can you see my screen? Hello? No?
Yes, ma'am.
Okay, but still in presenter view, yeah? Okay. Okay, can you see my screen now?
It's pitch black right now, ma'am.
Full screen?
Yeah,
It's black, ma'am.
it's black, ma'am.
Oh, black. Okay. Blah, 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 blah. Stop share. How about this one? Okay. Still, let's try, shall we? Okay, so this one is the TX diagram analysis. Okay, can you see this the full screen now?
Yes, ma'am.
Okay, now now let's have a look this diagram analysis, yeah. Okay, so let's say we have oops, this one. Let's say we have 2 feet. Okay, so maybe I can make some sort of box. Okay, so I have a feet 1. I have the feed 2. This is WAP, yeah, vapor. And I have a feed 1. Okay, so the feed 1 is a liquid, cair, yeah. The feed 2 is in the vapor. Okay, and then we heat it up, the feed 1, up to this one. Okay, so the feed 1 would be saturated liquid. Okay, and I also heat it up, just cool it down F2, so it's become in this one here, which is saturated vapor. Okay, so just imagine that I have a saturated vapor, and also I have a saturated liquid. Okay, right. And after that, let's say I have a similar amount. For example, this is 100 kilogram, and this is 100 kilogram. Atau maybe more, yeah? More. Just use the more. Okay, so I have 100 mole of vapor and 100 mole of a liquid. And then I mix them together. Okay, I mix them together. So, so what do you think about what happened in the mixture? Can you predict where is the points for the mixture? Is it here? Is it there? Or is it in the middle?
In the middle, ma'am.
Yeah. First, we need to look at this line, yeah, because so usually in the class I will use penggaris, yeah, the ruler, and then I will try to find in this line which one that has the similar length, ya, mana yang panjangnya sama between this area and that area. Why? Because we're gonna use left rule. Yeah, if we have the amount of liquid and amount of vapor, if we so this is the vapor, sorry, this is the liquid and this is the vapor. Yeah, nanti. Okay, then we have to find which one around area. Maybe in the middle here. Okay, just to make sure, you have to use your ruler. Yeah, find with your ruler which one, where is find the length of A and B should be the same. Yeah, the length of A should be the same, so then it should be really in the middle. Okay, so then we mix them together. Okay, now let's say this is the points. Okay, let's say this is the points, and then here you can see that the length of A and the B is looks almost identical. Yeah, 50%, 50%, 50%, 50%. So then you have the point 3. Yeah, so then I'm gonna write it again. So I have a liquid, which is F1, and also I have a vapor. Okay, and then I'm gonna put it into one chamber, and they're gonna mix them together. Yeah, they're gonna mix them together between the liquid and also the vapor. The liquid comes downwards from up, and then the vapor comes upward from the behind that one from the bottom, and then they gonna mix them together. And after they're mixing, if they have a complete mixing, they will have a new equilibrium. Yeah, and those new equilibrium will have a new composition. Can you check what is the composition of these two phases? So this one is going to be how about this one?
Liquid move.
Yeah, good. So then you will end up with a composition of liquid. Yeah, and then you're going to end up with new composition of vapor. So if you think about it, after they mixing together here, they will leave a new vapor that have a composition or maybe 0.6. Nah, sekarang dia punya 0,6 ya, 0.6. And the remaining liquid will have around maybe 0.2 XL to 0.2. Okay, so then you and then after it's mixing, of course, when you open the chamber, the top and the bottom, of course, the vapor will go upward, ya, akan keluar, and then the liquid would go, will leave this chamber. Okay, so this one is one stage of equilibrium. Okay. Oh, that's so that's good. So from 0.4, I can enrich my my composition into 0.6. Okay, but if you think about it, how much the remaining vapor do you have? How much the vapor do you have? So we start, yeah. So start we have 100 kilogram. 100 mole, and this is also 100 mole, because this is the same, yeah, it is also still 100 mole, but then for this case 100 sorry, this one, yeah, for the vapor, yeah, 100 mole, and then the component A would be 0.6 from divide by 100, yeah. So 0.6, so that would be 60 mole. Okay, so then we get, yeah, we'll get quite big, quite good number, yeah. I'm just gonna be like this. Okay, so in a sense, it is good because we have 0.6 for the composition, but then we only end up with 100 mole, ya, setengahnya dari yang tadi, ya, because from the initial one, which is 200. Okay, so and then I said, no, I'm not satisfied with 0.6. I need to do more. I need to get more more purity of A. Yeah, I want to have a more. So I will do one more. Let's have a put it there. Let's me cool down a little bit. So let's this the vapor. Let us cool it down again. Maybe around this area, yeah. Let us cool it down up to 100, around 50% can go into the vapor phase. So if I cool it down, half of it, yeah. If I cool it down, it will go to another 2 phases, maybe around that area. Okay, and then I will have a new maybe 2 feet, yeah. Another composition there. Okay, but how much the remaining of vapor that I have? Because half of them, so 50 mole, ya. Jadi setengahnya lagi, because another 50 moles goes into the liquid phase. Okay, so in here I have now 50 mole of feed, and then the YA maybe almost 0.8. Okay, yeah, 0.8. And then yeah, so the here I have a more pure, a purer A component A, but my amount would be less, yeah, from 200. So it's just only 50 mole. Okay, and then we can do that again. So we can do some more, yeah. So we can do, if you make it smaller, and then you can go to that way. Okay, so so the idea here, so this graph is just basically tell you if you lower the temperature, you end up with more pure of vapor, yeah, higher composition of vapor, but you get less vapor, isn't it? Because in the graph in the Lever's diagram, this is the amount of the vapor that you have compared to the liquid. Okay, so the drawback, so the trade-off, if you want to have a high composition of A, if you cool it down a little bit, but then the vapor is very small. Okay, something like that. Okay, so this is the idea. So that's why in the distillation, we may want to cool it down a little bit, and then we got the new one, and then cool it down a little bit, and we got the new one. Okay, but then here the question is, but that means that the one that that we have is going to be very small compared to the feed. Mubazir, yeah. What's mubazir? So that means there's so many liquid that must be discharged, yeah, because we only have a few mole, for example, 50 mole from 200 mole in the beginning. So that's why we're gonna go into the next slide, and then that will tell you what is the principle of distillation that we have. What is the principle of the distillation that using a multi-stage distillation to PTX diagram analysis. So let's see the multi-stage equilibrium. Okay, give me 1 second. So let's see segment 6 and segment 7. Okay. Okay, it's only 15 more minutes, so I'm just gonna a little bit speed it up, but later on we will repeat it again next week. Yeah. So the principle, I won't make it full screen, so yeah, just to make it easier. So the principle of multi-stage distillation is actually we have the feed, and then we heat it up. For example, this is the liquid. We heat it up to this stage, and up to 50% become to make 50% become a vapor, okay, like this one, okay, 50% become vapor. So for example, here this one is the 200 kilomole, and then make it 50% become vapor, 50% become liquid. So then we have 100 over here, okay, and then this 100. So for example, this is from 200 become 100. After it goes into the vapor phase, we don't catch it. We don't just cool it down everything, but let's try to cool down a bit. Let them to cool down a bit, up to half of them goes into the liquid phase. Okay, so here we have a new second stage. So if I can draw in this area, so first we have maybe I'll put it there. Yeah. So first I have one stage here. I have a feed, and then the feed, let's say the feed is liquid. Okay, and then I'll put it into an equilibrium, and then it become a vapor and also another liquid. Okay, and those vapor here go to the this is what one stage, yeah, and the second stage here I put it into another chamber of a chamber of equilibrium. Okay, so from 100 kilomole, I make it, I just cool down a little bit, just cool down a little bit up to 50%. So maybe, and then, so we can get a new vapor, while then also release the liquid as well. Okay, so this is the liquid. So this is a stage 2. Now, how much the vapor that we have now? How many mole?
0.6 something, 0.625.
Oh yeah. So that is a component, yeah. So now we have the component where IA is 0.63, let's say. But how much is the V? V now, the amount of vapor we have. Only half of them, yeah?
Is it 50, Bu?
Yeah, 50, good. Okay. And then we do another one. Oh, go again, yeah. So, and then we do another one. Let's say we put it plus here, and then make it another one there. And then let's put another stage. And then we will have maybe up to the V is become 25. And then, but you have a higher A, which is maybe around 0.7 something. Yeah, 0.7. Okay, so you done that. So this is gonna go to stage 3. And then go, and then you have more up to the maybe stage 9. Okay, so once you go into the stage 9, if for example this is the stage 9, you end up with the vapor. The vapor is very small, then of course when you heat it up something here, you need heat. Yeah, when you cool it down, you need to remove the energy. You need to remove the heat. So how to remove the heat is actually we're gonna put a little bit of liquid over here to cool it down. Okay, put the liquid and then to mix over here. So put some liquid and then mix to over here, just to make sure that they give the heat inside the vapor for the vapor is cool it down. Okay, so if I go back to my drawing before, so because when we cool it down, we need heat. We need to remove the heat. We can add some liquid from outside, or maybe later from the condenser liquid to absorb the heat. Yes, so absorb the heat from here, and this is also to absorb the heat from previous ones. Okay, and then in the stage, it would be looks like this, where the green, the orange one is actually the flow of the liquid. Okay, so the liquid is gonna put it back like that, and this one is called the enriching. Okay, so this is called the multistage equilibrium. So how we increase the composition of the vapor A that we want by cool it down a little bit. How to cool it down is by putting some liquid inside the chamber and then mix it. Yeah, mix it, and then it will leave a new composition. For example, this is stage 1, tahap 1. We have a vapor and we have liquid there. Okay, and after that, they will end up with stage 1, and then we'll end up with new equilibrium. Yeah, so this is if it is stage 1, this is X, yeah, because of cairan liquid, X1 yang keluar dari tahap 1, the one that leave the stage 1, and this is, we call it X1, Y1, which is the vapor that leave the stage 1. So this one and this one is in equilibrium. Okay, and then let's go to the stage 1. In the stage 2, for example, in the stage 2, we have liquid. Yeah, we have liquid maybe from stage 1. From stage 3 maybe, and then we have vapor from stage 1, and they're gonna mix them together over here, and they will end up with Y2, yeah, new vapor and then new liquid, like that. Okay, so the function of stages, this is called multistage equilibrium. The function of stages is to as a contact between a vapor stream and from the bottom, and also the liquid from the top, and then the contact will cause diffusion process between vapor and the liquid phase, and then they're gonna mix them together, and there would be like a froth, busa, yeah, or they're just gonna mix them, swirl them together inside those chamber, and then after that the new equilibrium will leave the tray. Okay, so that's how we're gonna define it. Then we're gonna leave the new equilibrium, yeah, for example the Y1 and the X1, and then to separate the resulted vapor and a liquid, and it is so the vapor flowing upwards, and the liquid will flowing downwards. Okay, lastly, this is called the enriching or rectifying section, where the feed is vaporized up there, while the liquid, it came from, we called it from reflux, yeah, dari cairan reflux. So some of the vapor, we cool it with overhead condenser, and some of them we got it as a distillate. Well, not all of them we took it as the distillate, but some of them we returned back into the fractionation column into as a reflux. All right, so I think that is the principle of enriching section. Yeah, so if you're still a little bit confused, that's fine. Just put it back for a while, and then check again next time before next week, yeah, before Thursday, and then we will continue it next week. All right, almost 11 o'clock, so I'm gonna